Hi, everybody. So, previous lecture, we talk about introductions to bio-separation process. But now we will focus on the separation of solid from liquid. This is the first equipment that we will talk to you. And it includes like filtration and centrifugation. The first one is filtration. Filtration is the equipment used to separate solid from the liquid. That's like when we ferment material, and then we get the fermentation board, and then lots of component mixed together. And also our product is mixed in the fermentation board. Solid is maybe microorganism, maybe enzyme, or it's maybe like the cell debris, something like this. The first step, we have to separate solid from the liquid. That the most common one is the filtration. By the function of the filtration, it is separated by forcing the fluid through a filter medium or filter coat, with the solid will retain in the filter coat or filter medium, and solid will pass through the filter coat. Mostly the solid will deposit on the filter. We can call it is like filter cake. The filter cake will increase in depth. That's why when we increase the flow of the fluid across the filter. Okay, the pressure difference across the filter to separate fluid from the solid, we call it the pressure drop. The pressure that's like to for the liquid pass to the filter cause of filter air, and solid will deposit in the filter code, we call this pressure drop. And for this class, we will talk about the separation or bio-separation, and mostly we will consider on the fermentation board. That the fermentation pot is quite difficult to filter because it is quite like the viscous fluid. Because of a very small molecule like microorganism or enzyme, it's quite very small size. And the nature is in the gelatinous, and also mostly the fermentation board is considered to be the viscous or non-Newtonian fluid. That means it's difficult to separate. This is the function and the common fluid solid system in the bio-separation. This is show you right the figure or the function of the filtration. Okay, this direction is direction of the fluid flow. Please remember that the fluid is include like the solid, very small solid, and fluid as I mix together. And we would like to separate the solid from the liquid. For this work, we use the filter coat. The filter coat is in the filter coat we have like some the hole. That's in the hole, the solid will cannot be passed to the hole. Only the liquid pass to the hole of the filter coat. And the liquid that's out of the filter coat, we call this filtrate. That's right. And solid that deposit in the surface of filter coat, we call it is like the filter cake. And smoothly, we would like to increase the efficiency of the filtration or the separation. We may add some filter aid. That's right. Filter aid is the solid that can be help for improve the separation. The filter aid mostly in this work we use like diatometers, which is far widespread used in the fermentation industry. Right, it is the back one. It is the filter aid. Mostly we coat the filter aid in front of the filter course, and then when we separate the solid from liquid, we flow the suspension or the mixture in this direction. In this direction. And the circle is the solid that we would like to remove. The solid can attain or can deposit in front of the filter aid, but only liquid pass to the filter core. This is the characteristic of the filtration. And cake being the solid of yeast or enzyme or another like bacteria something, that's right, is deposit in front of. And also we call the cake is mixture of filtrate and solid. Filtrate mean the clear liquid that's part to the filter. Okay. This is that I talked to you already from the previous picture. That's like the fermentation process may be preceded by improved filtration characteristics. Maybe we would like to heating to a nature protein to enhance the filterability of micelle growth, such as penicillin production. And alternatively, electrolytes may be added to promote coagulation of colloid into larger. If very small particle is difficult to separate, and then we can improve the efficiency of separation by increase the size of the particle that can be coagulation by use some electrolyte add to the solution, and then some particle will come together in a bigger size. That's right. And also bigger size is heavier and denser particle. That's easier to filter. And the last one, the easy to filtration is also affected by the duration of the fermentation. That's right. Yes, affect the composition and viscosity of the medium also. Okay. This is the configuration of the first one of these filtration equipment. The most common one for the filtration used in bioprocess industry, we have at least two kinds of the filtration equipment like press and flame filtration and rotary filtration. In this picture, I show you the first one is the press and flame or press filter. But like for this kit, we have two equipment mixed together, like press and flame. That's right. And flame for it, we have right. This is the direction of the suspension of the mixture flow in this field. That's right. This is press. This is this press, this frame, press and flame, and allow the plate we coat with the filter. Yes, I did a filter of the plate. Press frame, something like this. This is a filter. And then the solution flow in this direction, come to this state. First state, second state, third state. Yes, come to this state. This is the filter around it, the filter. The solid can deposit on it and liquid can pass through the filter and collect in this direction. Yes, so in this direction, and also some in this direction or in this direction. Is it this? And this is the collection of the clear liquid. It is a feed solution to write this. Okay. And also, we show you right the equipment in our pilot plant in the Olifari our project in the our pilot plant. This is the present frame in our university. This is we have the present frame with filter course. Yes. This is direction of clear solution flow out. Yes, and mostly after filtration, the cake or the solid will deposit in the front of the filter course. Like this. For example, the equipment in our university. Another one that's most common used in the opposite that is rotary drum filter. Rotary drum filter. They show the rotary drum filter. We have at least 1, 2, 3, 4 sections for the rotary drum filter. In the first section is the section of the filter. Filtrate. This is the filter course. Filter course is cover the rolling like this. That's right. This filter course. And this is the reservoir. This is the fluid that we would like to separate of the solid out with this. And also if we make it as vacuum, if we make this as vacuum, that's right. Liquid before got the filter, got the filter in this, that's right. And then the equipment will rotate continuously. Okay. If they rotate until in this pass, the liquid will fall at the filter, got the filter, and liquid can fall at the filter and get filtered. and the solid will deposit in front of or in the surface of the filter coat. That's right. And then after the filter section like this, rotate of the liquid until it enlists in this section. For this section, we will wash by water, something like this. That's right. Cake will be washed by water. We wash by water. That's right. And then it's loaded continually in this section. In this section, the water in the filter cake will dewatering. We dewater, remove the water out of the cake. And until the filter loaded continually in this section, we have a knife scraper, a knife or scraper. This is the filter cake will be removed from the surface of the filter. And then we get this, the filter is, there is no solid or filter cake in front of the surface of the filter. Okay, if the equipment rotate continuously until it's suspended in the liquid. And this is the filtration occur again. That's right, filtration occur again. The liquid can pass through this, and solid can deposit on this, and then continually rotate, watching, and then continually rotate, dewatering, and then to remove the solid. This is the rotary drum. We call it the continuous process. It's mostly used in the industry. Right, we have 4 sections. Like the first section is filtration, and then watching, and then dewatering, and the last one is remove the solid. That we can use this filter continually. Okay. This is the example of the 2 kind of filtration equipment, that's plate and frame filter and rotary drum vacuum filter. And also, we show you the equipment, and then now we will talk about the filtration theory. Filtration theory, usually we talk about the rate of filtration. The rate of filtration that we consider the rate of the filter. Most filter is the clear liquid that's passed through the filter course. Mostly we can express the volume of the filter, VF. That's right. VF is a function of pressure drop. It's a function of viscosity of the fluid. Mu F is the viscosity of the fermentation mode. Alpha and Rm. Alpha is the specific weight resistance, the resistance to the flow of the liquid. Rm is the medium resistance. Medium, this is we call the filter course or filter medium. And also A is the filtration area. If we talk about the filtration area, if we consider the filtration area of the rotary drum, the filtration area is only considered for this case. In this area, this area is not for filtration. The area of filtration, if we consider now, is only in this zone. That's right, only in this zone. And if for the plate and frame, okay, all of the area, that's right, for this. And for rotary drum, only for this. Okay. It is the area of the filter. Okay. We can express like the relation between pressure drop, filter rate, that's right, dV by dt mean filtration rate. That's right, filtration rate. Delta P is the pressure drop across the filter medium. That's right, input and output. Time is the time. Delta P is pressure drop. MC is the total mass of solid in the cake. Mostly in the cake we have 2, right? Solid and liquid in the cake. MC is the total mass of solid in the cake, only solid. Alpha is the specific cake resistance. Rm is the filter medium resistance. Okay, for this case, Rm include the effect of filter coat and any particle within the during initial state of filtration. The dimension of the Rm is expressed in length with the mass. That's right. Its dimension is length with the mass. dV by dt is filtrate flow of filtration. That's filtration length, something like this. Okay. It's mostly in the filtration we can neglect the effect of filter medium resistance or Rm. Why we can neglect? If you consider the first figure like this. This is the filter medium. And then you compare to the filter cake. The resistance to the force mostly occur in the filter cake because it's quite thick when compared to the filter coat. That's mostly in operation we can neglect the effect of RM or resistance due to the filter medium. What we consider resistance due to the cake. This is for the assumption. Okay, and then we will consider the cake. Mostly we talk about the resistance to the cake. And we have at least two kinds of the cake: compressible cake and incompressible cake. That's right. For compressible cake, we can relate the cake with the pressure drop. Incompressible cake, that the resistance is not depend on the delta P. But compressible cake, the cake depend on delta P or pressure drop. Both we can express or we can show the relationship between alpha or resistance to the cake due to the cake equal to some constant multiplied by pressure drop over S. Because S is the cake compressibility and alpha, that is the constant, depends on the size and morphology of the particle. That's mostly the compressibility and the constant is mostly depend on the morphology, the shape of the solid, morphology, the shape of solid, and also the size of the solid. And then we can relate or we can express the alpha is a function of kVA squared 1 minus epsilon divided by epsilon over 3 rho p. That's like A, what is A? What is kV? What is epsilon? kV is the shape factor. The factor that depends on the particle. A is the specific surface area of the particle, and epsilon is the porosity of the cake. Rho p is the density of particle. That's right. And also we can define the epsilon and A. A is the surface area of a single particle divided by volume of a single particle. The ratio of surface area and the volume of the particle of the solid. And the epsilon, the white fraction. Epsilon is maybe calculated from the volume of the cake divided by volume of the solid in the cake. So volume of the cake minus volume of the solid in the cake and divided by total volume of the cake. That means the Y is mean like the white, that is mean equal the solid. This we consider only the liquid in the cake. That's mean the liquid in the cake. That's like the white fraction. Okay, how to improve the rate of filtration? If we consider the equation like this, if we would like to increase dV by dt, okay, you can increase delta P. You can decrease Rm, you can decrease alpha, or decrease mu. This is the technique to improve the filtration rate. And the first step, you can increase the filter area. If you increase the filter area, you increase the filter area, you remove a further, to this, we get multiplied by A, okay? A increase, dV by dt, okay, increase. This is common sense. And the second technique, you have to increase the filtration rate by increase the filtration pressure drop or delta P. This delta P, sorry, delta P. And also you can reduce MC, you can reduce the mass of cake, reduce the viscosity, or reduce the specific cake resistance. How to reduce the specific cake resistance? If you look at this, if you would like to reduce the specific cake, you have to increase the porosity, epsilon, reduce the shape factor, and reduce the specific surface area, or A. And then the technique to improve the filtration rate. Okay. If we consider again to the MC, MC is the mass of the cake. The mass of the cake can be calculated by the multiplication of concentration of the absolute per volume of filtrate with filtration rate. Filtration rate. And then you can express in this term. This is this equation. And then you can group some term like VF divided by A delta P and mu f Rm divided by delta P. If we substitute MC, that's right, from previous equation, this is MC. You substitute MC by C Vf, you get this equation. You get this equation, and then you rearrange and integrate from the start of the filtration until the final filtration, from T0 to T final, from V0 to Vf, like this. And then you get the time and the area of the filtration as a function of filtration for the flow of the filtration. And also the function of alpha and Rm, alpha and Rm. For this case, we can call it a constant. This constant due to the alpha, this constant due to the Rm. So we can call this is something like this. We can learn like it. Okay. We get T over Vf equal to this term and this term. We reduce this term into K1 and it's K2. K1 is the constant with respect to the alpha. Alpha is the resistance of the cake. K2 is the constant related to Rm, is the related to the medium resistance. Okay, and then we get T over Vf with a function of K1 Vf plus K2. Then we can consider it is the linear equation. T over Vf is the dependent variable and Vf is the independent variable. And then if you know time, you know flow rate of the filtrate, you can calculate K1 and K2. And then also you can calculate alpha and Rm. That's right. Alpha is the cake resistance, Rm is the medium resistance. That's right. From the relationship of this equation, and then you can calculate K1, K2. If you know K1, you know K2, you can calculate the medium resistance and cake resistance. Okay. For this example, right, we will consider like 30 milliliter sample of growth from penicillin fermentation. We use the filter to separate the solid from the liquid by using like 3 square centimeter filter area at the pressure drop of 5 psi. The filtration time is 4.5 minutes. From the previous study, it showed that the filter cake of penicillin is significantly compressible with H equal to 0.5. Okay, this is the previous experimental result. And now if we consider like 500 liter growth from a pilot scale fermentation, we use to filter in 1 hour. The question is, what size filter is required if the pressure drop is 10 psi and 5 psi? For this example, we neglect the medium resistance or Rm. That means we cancel this term. We cancel this term. Okay. Okay. For this case, we know the information from the lab scale, and then we will scale up to the large scale or pilot scale. Okay. The first step, we have to calculate some parameter from the lab scale. Okay. For this case, we know, right? This question we can cancel Rm term. Then we get T over Vf equal to mu f alpha c divided by 2a squared delta P. And then you can rearrange this equation. You get mu f alpha c equal to this term. We have to rank this term because we don't know mu f, we don't know alpha c. But we know A, we know T, we know delta P, we know Vf. Okay, from the data, from the experimental data, A is 3 square centimeter. Time is 4.5 millimeters. Delta P is 5 psi, and the filtration rate is volume of the filter. That's right. Vf is the volume of the filter is 30, and then you can calculate this term, mu f alpha and c equal to this. For this system, mu f alpha c is constant. That's right. For this system, mu f alpha c is constant. Okay. For that case, you can calculate the area of the parascale, from this equation. You can realize a square equal to this equation, and then you can take the square root, you get a equal to this term multiplied by VF. VF is the volume of filtrate. Okay. For the large scale, the volume is 500 liter. 500 liter. 500 liter. And we know delta P. That's right. We know delta P. We know time. We call the time is 1 hour or 60 minutes. That's right. We know time. We know delta P. We know this term mu alpha C. We know this term is equal to this. This is mu alpha C. Okay. We know this term. We know delta P. You know T. You know VF. You can calculate it. Okay, the first question for delta P equal to 10 psi. You substitute delta P. You substitute mu alpha C. You substitute time and V, and also you use the unit conversion. You get A equal to 1.15 square meter. This is for 10 psi. And another question is for 5 psi. The same equation, you only substitute 5 psi, and other term is the same. You get 1.37 square meter. Okay, for this case, we can conclude that the pressure drop increased the area required by only 20%, because at 5 psi cake is less compressed and more porous than 10 psi. Because at 10 psi we need only 1.15 square meter. And if we reduce the pressure, we need higher area. This is for the effect. And also for this example, we show you how to scale up. If you know the large scale, okay, you can use the large scale information to make the large scale filtration. In conclusion about the filtration in general, right, the fungal mycelia are filtered relatively easier because the mycelia is filter cake has significantly large porosity. And yeast bacteria are much more difficult to handle because their size very small. It's very small size, it's difficult to filter. In this case, another technique is better. Maybe you would like to add some electrolyte, add some chemical to precipitation, right, to make the precipitation, to make the solid increase in the size and then easy to separate. And the alternative filtration method which eliminate the filter cake are becoming more accepted for bacteria and yeast separation. That said, microfiltration is achieved by developing large free velocity across the filter surface, while the velocity normal to the surface is relatively small. Okay. And build-up of filter cake and problem of high cake resistance are therefore prevented. Microfiltration is not covered in this step. Further detail, okay, we will talk this. Moreover, if the very small particle size, we have to treat the mixture before filter, right? We can use the precipitation technique or we can use the solidification technique. For these two techniques, we can increase the size of the particle before separate. Maybe if the size is very large size is maybe like heavy, and then we will separate by the gravitation. This is easy to do. Okay, we will stop like this lecture, and then we'll continue for the next lecture about centrifugation. Centrifugation is another technique to separate the solid from the liquid, especially for the small particle size. It prefers centrifugation. Okay, see you for the next lecture.